Welcome to the course Corrosion for Engineering Materials. I would love to give credit to Prof. Anthony Andrews in the Department of Materials Engineering. He was my lecturer for this course. So now, we're going to talk about introduction to corrosion, basic definition of corrosion, and some effect of corrosion. So let's look at the outline of this course. Now, the unit content is going to talk about understanding what is corrosion, the effect of corrosion, cost of corrosion, why metals corrode. We are going to look at some concept of definition of corrosion, classification of corrosion, and factors influencing corrosion. Now, let's get into it. One may ask, what is corrosion? And when we talk about corrosion, corrosion has a lot of definitions. But with this, we're going to look at it's an undesirable deterioration of a material due to a reaction with its environment. So when a material reacts with the environment, there's a change in the material which affects the structure. And when the structure is affected, it also affects the property of the material and the performance as well. Now, physical deterioration of material and its property and now its performance, as I said, that when the structure of the material is affected, it also affects the property of the material, which also tend to affect the performance of the material. Now, why is it that corrosion is mostly refers to metal? This is because metal are highly conductive. They can conduct electricity. This is the case that they allow electron to flow through them. And also, they also undergo electrochemical reaction. Now, we only know that only metals undergo corrosion, but that is false. We have other metals, other materials that undergo corrosion. We have the ceramics, we have polymers, and we have composite. Now, when ceramic, polymer, and composite undergo corrosion, we term it as degradation. So, ceramics, polymers, and composites degrade, but metal corrode. Let's take note of that. Now, we have some pictures of corrosion, and at the end of this course, you know how all this came about and what are the necessary things you need to do to prevent corrosion. So, this is a picture showing one corrosion here. This is another corrosion. You have a corrosion material, corroded material here. There is also a tube or a pipeline, but you can see that we have corrosion on the nut, right? And these are all electrochemical reaction between the pipeline and the nut that you get to know that. And here we have some corrosion happening here, right? Now we move on to some effect of corrosion. We know that this is a bridge, and when a bridge fails, you know what happens. There's a cost, there's environmental pollution and everything. So this material, this is concrete made with cement and other components, and we have reinforcement inside, which can be a metal. And when this reinforcement is exposed to the environment, we have something called a concrete corrosion. Then the metal undergo degradation or corrode, and then failure happens due to the structure being altered, affecting the property and also the performance of that material. We also have this bridge also collapsing due to corrosion. We have another one, same thing, some effect of corrosion, and these are some cost. It comes with costs when corrosion comes in. There's high amount of money raised to prevent corrosion, and also when it happens to, there's a lot of money involved. So now we're going to look at some effect of corrosion. The first one I'm going to talk about is waste of resources, energy, manpower, and material. Imagine that you have made your bridge and everything is nice, and within several months that bridge goes down. You see, can you picture that? You've lost material, manpower, and energy. Note that from here, 1 ton of steel tends to rust every 90 seconds. Wow, that's so powerful. And 380 kilogram of carbon dioxide emission for every ton of what? Steel. So that means that this also can lead to what? High rate of what? Global warming. So global warming, corrosion can also lead to global warming. We have 50% of every ton of steel is used to replace. So 50% of every steel is replaceable with corroded steel. and that's a lot of cost. Yeah. Let's look at the financial loss. We know that insurance company, when you have this and you insure your product and then it fails, the insurance company need to pay about, this was estimated in 1990s and it's about 91 billion. Wow. For natural disaster and direct cost of corrosion. Wow. For maintenance and this one is 276 billion. Ha! For only corrosion. You see that? So the effect of corrosion is very high, right? We have 25% of corrosion costs can be saved using existing technology. So at the end of this course, ways in which you can use to protect and build up to prevent corrosion from happening or to reduce the rate of corrosion. Let's look at the cost of corrosion. With the cost, we have two. We have the direct cost. When we talk about direct cost, it is what? Quantified. So you quantify it. You know that you are doing it with a specific amount of money. So replacement of damaged or corroded equipment, use of corrosion resistant alloys. So this, you are doing it to prevent or to reduce the rate of corrosion. That is, you are doing to reduce the what? Reduce the corrosion rate, right? Or you are trying to prevent the corrosion from happening. That is why you do the direct cost, right? And use of coatings and inhibitants, electrochemical protection like CP, cathodic protection, or sacrificial anode. Now we move on to indirect cost. When they were indirect cost, you don't know that whether it will happen. You don't know. Suddenly it happens, and in a plant, when it suddenly happens due to corrosion, we have loss of production, downtime, and downtime is the time taken to repair the equipment which has been corroded, or the equipment which cause the loss of production due to corrosion, because you're going to lose time. And it takes a lot of time. Maybe it's essential part of the plant and it's undergo corrosion, and then maintenance is not done, and then suddenly just breaks down due to corrosion. There's loss of production and loss of product due to leakages. So we have a pipeline and we have some corrosion happening. You know that at certain points leakages will happen and you'll be losing product. Loss of efficiency due to corrosion. Yes. Over design. Yes, over design. Designing with, maybe they give you as a designer or a contractor, you are supposed to design, or as an engineer, and you know that some designs are not necessary to be part of the engineering structure, and then you just, for your own benefit or for something, for I don't know, for fabrication or something, then you just add different components to it, which you don't tend to look at the effect of that component, and at the end it leads to corrosion, and then it leads to disaster, loss of life. As you can see from the bridge, if this bridge fails, explosion, fire, people will die. They will die, lose their life. Let's move on to when we talk about material degradation. Mechanism of material degradation can either be physical or chemical process. And there are four basic classification, which is by direct mechanical actions, which can be stress, loading, how the stress is being loaded on the material. We have this cyclic loading. We can get fatigue, corrosion, stress assisted corrosion, and the rest. We have by heat or radiation. You know that when there's heat, high temperature can accelerate chemical reactions within the material, and it can cause it to break. We have presence of chemical reagents. We have some reagents which are very corrosive, especially the acid reagents. They're very corrosive, and when they come in contact with this material, it changes the structure of the material, and then when the structure changes, it affects the property and affect the performance, and then leads to corrosion and this. And synergetics of interaction of two or more mechanisms, you combine the two of them together, and that one is more dangerous. Yeah, it's more dangerous. Now let's look at still under material degradation. Materials degradation or material degradation can be defined in terms of loss of performance of an engineering material or of an engineering system, because the material have lost performance. It cannot perform its intended action or if its intended function, right? And with this, we know that it can lead to loss of mechanical strength, the tensile strength, all that, yeah, that one. Due to what? Being exposed, the component being exposed to what? Corrosive medium. We have loss of efficiency, yes, and also loss of lifetime. Let's look at this. Reasons why materials undergo degradation. we're going to talk about the environmental factor. So let's take heat. Now you know that high temperature can what accelerate chemical reactions within the material, causing it to break down or lose its what structural integrity. So when there's high temperature, that means that it can lead that. But there are I can tell you that for the high temperature issue, there are certain concepts depending on the type of material you're dealing with. It could change, right? And the chemical and pollution, contact with chemicals or pollutants or acid substances can corrode or erode materials, weakening them over time when they are exposed to it. Yes. Even water, that's moisture in the presence of oxygen, you know that it can also do that because it's a chemical, right? We have the mechanical stress or action. And when we talk about mechanical stress, physical forces such as friction, pressure, or what repeated stresses, which is fatigue, can cause wear and tear, leading to fracture, and what formation. You know that we have stress-assisted corrosion, which is caused by what mechanical stress, how it applies to a material. We have radiation. Radiation is like exposure to radiation, such as the UV radiation from sunlight or ionizing radiation can cause molecular damage and degradation of the material. So with this radiation, it's internal. That is internal. The system is internal. So you will not see it, but the material will be undergoing corrosion and it affect the structure and then long to them. And we have the bacteria and the fungi. Microorganism can what colonize materials, leading to a biodegradation or microbial corrosion, particularly in inorganic what, particularly in organic materials like wood and fabric. So here you know that wood and what fabric, we have a microbial corrosion in them, right? It can happen, right? Yeah. Now let's look at one important thing. Why do metals corrode? Yeah, that's the question. Why do metal? The first thing we're talking about is that metal corrode due to chemical pollution and contaminants of the environment. So when the environment is introduced, we have some pollution or pollutant in the environment, which then come in contact with this material, or in this material, talking about metal. The metal is also reactive. It reacts to the pollutant, and then corrosion sets in. Ooh. And also chemically unstable in the environment. Metals are chemically unstable in the environment. Always metal want to be, when talk about metal, they are always they wish to be in the stable form. So anything that, if they are unstable and then there's anything that will make it stable, it just go. No, we have metallic elements occurring abundantly in nature in their ores. That's the oxide. So when there is in the material, engineering material, and then there's this factor that knows that when it comes in contact with that metal, it can change it to its stable state. Everyone's going to be stable. So you find where it can be stable, and when it becomes stable, boom, corrosion sets in. So we have something called extractive metallurgy in reverse. Let's look at extractive metallurgy in reverse. So this is extractive metallurgy in reverse. We have our mine ore. This is the ore. We want to extract iron from it. So we have the iron ore. We do steel mill, reduction, refining, costing, rolling, shaping. And then we have one as sheet. We do one as sheet and we do one as pipe. This sheet is used for making car bodies, right? And it's reacting with the atmosphere. And this pipe goes underground, which happens to react with the soil and water. And with time, it comes back to what? Hydrated iron oxide, which is rust. So metals always want to be in their stable state. So if there are conditions which will make the metal to be in their stable state, why not? They react and then they become stable state. And when they are in their stable state, we call it rust. This is rust. You see? Yes. Now let's look at another one. So we have this picture. We have this. This is an ore. And then we have this bloom and the billets. And then you see it come back to its original. So you see the color of this. We have the color. So this is reverse metallurgy in reverse, extractive metallurgy in reverse. Because you have extracted the material, you have this, you use it for engineering material, and when they are conditioned, which will facilitate corrosion, and it's come back to this. You see? Yeah. Let's look at the cycle. That's the corrosion cycle of steel. So now we have adding of energy. We add energy to the mining, or heat and everything is added to extract it and make it what a finished steel product. And then when it reacts with the air and atmosphere, and it corrodes to form rust, come back, so it gives out the energy. So adding energy, certain factors also makes it what give out the energy and turn into rust. As simple as that. Now let's go to definition of corrosion. Now, when we talk about corrosion, we have the practical definition, we have the scientific definition, we have the combine, whereby we combine the practical definition and the scientific definition. The practical definition is that it's a tendency of a material to revert to its native or natural state. When there are conditions available for it to revert, it does it, because everyone wants to be stable. Don't you want to be stable? You want to be stable in financially and everything. You want to be stable. That's the same thing. Metal also want to be stable. So if there's a place that they are unstable and there are some conditions which will make it stable, why not go for it and they become stable? And then the scientific definition is that it's electrochemical degradation of a metal as a result of reaction with its environment. So when a metal is here and you have some electrochemical reaction from the environment happens to the metal, then it reacts. This is change in potentials, and then corrosion sets in. The combined definition is a destructive attack on a metal. But let's note that it's not only metal that corrode. I explained that we have other materials, ceramic, polymers, that composite that degrade in the form of, that's how they corrode. We call it degradation. By electrochemical reaction, which with the environment, corrosion retains the metal its oxidized state or combined state in chemical compound that are similar or even identical to mineral which the metal are extracted. So then ion reacts with, this is ion, then it reacts with oxygen, then it's hematite or magnetite, because this is an ore. You have this extracted from engineering material, then it reacts with the oxygen, and then it comes back to its ore state. That is how corrosion is. That's why it's a extractive, right? It's extractive metallurgy in reverse. Now let's look at some definition, right? We have the aqueous corrosion, and with aqueous corrosion, this is zinc reacting with hydrochloric acid, giving you zinc chloride and hydrogen gas. We have also aluminum reacting with water to give you alumina and hydrogen ion. This is an aqueous solution. We have oxidation. As I said, if ion react with oxygen, it's come back to what? Hematite, and this is the ore of it. Are you getting it? Now at high temperature, that's high temperature corrosion. When ion reacts with carbon dioxide at high temperature, we form what? Iron oxide and carbon monoxide. And this has been reduced to its native state. Let's look at zinc. That's the corrosion, zinc corrosion in what? Diluted hydrochloric. Now in this case, what we are going to talk about is we have what happens when zinc is immersed into what? Deaerated aqueous hydrochloric acid. When we say deaerated aqueous hydrochloric acid, deaerated means there is no what? Oxygen. There is no oxygen. So we are talking about deaerated, no oxygen. And with deaerated, you know that we are going to get this forming. We have the zinc, which is solid, plus 2HCl, which is aqueous, giving you zinc chloride plus hydrogen gas. This can be separated into anodic and cathodic reactions. So we are going to look at the cathodic and anodic reactions. So two reactions are very necessary. We have the oxidation reaction, which is the anodic reaction. So we have the anodic reaction, which turns out to be the oxidation reaction. And with anodic reaction, we know that zinc is being what? Oxidized to 2H plus 2 electron. So this is the what? Anodic reaction. And we have the cathodic reaction, which is the reduction reaction. The cathodic reaction. So this is the half reaction. And the cathodic reaction, since it's deaerated, there's no oxygen. And what we want is the hydrogen that's involved of what? Hydrogen. That means we're going to get 2H plus 2 electrons, giving you H2 gas. And in this case, this is for deaerated in dilute hydrochloric acid. Now, let's look at in the aerated. When talk about aerated, it means that there's oxygen. So the aerated, let's look at the aerated. So with aerated, presence of oxygen. Now you know that for the anodic reaction, always is expressed as what? M is equal to Mn plus Ne. So always, you know that it's going to give you something like this. So the anodic reaction, we are going to get zinc giving you zinc 2 plus what? 2 electron. Now for the aerated, the more concentration, what we concentrate on is the cathodic reaction. For the cathodic reaction, since it's aerated, that means that there's oxygen involved. So that means that in acid, we are going to get O2 plus 4H plus 4 electron, giving you. So in this case, this is the aerated dilute hydrochloric acid, presence of oxygen. So we have oxygen gas reacting with 4 moles of hydrogen ion plus 4 electrons, giving you water. So the overall reaction, you can know that you multiply 2 by this to make it 4, and then the 4 will cancel out, and you can find the overall reaction. Please kindly find the overall reaction and put it in the description. Please kindly find the overall reaction and check the comment section and put it down. Let's talk about, let me look about, before we move on, we also have the alkaline, right? Neutral or alkaline. So we are looking at alkaline. With alkaline, you know, this is for acid. For alkaline, the cathodic reaction is going to involve O2 plus 2H2 plus 4 electron, giving you 4OH. Let's take note of that. OH minus. So with the acid medium, aerated acid medium, there's oxygen inside, and this is how it happens. And aerated alkaline medium or neutral medium, we have this forming. Let's take note of these two. It's very important for this course. Now let's look at the atmospheric corrosion of iron. When iron undergo corrosion in the atmosphere, now we have that. Let's write the anodic reaction. We have the anodic reaction. The anodic reaction, we know that iron is Fe, giving you Fe2 plus what? 2 electron. Now the cathodic reaction. Now when we talk about the atmospheric corrosion, that means that there is presence of what? Oxygen. So we are going to do this in the alkaline medium, right? So in the alkaline medium, we are going to get that O2 gas plus 2H2 plus 4 electron, giving you 4OH minus. Now let's try to find the overall reaction. This, you are going to multiply 2 to the top. So when you multiply 2 to the top, you can cancel it out, and then this will be 2, this will be 2, and here will be what? 4. Then this is going to cancel this one, and then when you find the overall reaction, you're going to get 2Fe plus O2 plus 2H2, giving you 2Fe 2 plus 4OH minus, and this we term it as rust. This you go back and you do it like 2FeOH2, and this is rust. It's termed as the rust. So this, we did it in the alkaline medium, which can be neutral. That's neutral or alkaline medium. You can try it in the acidic medium, and let me see your answer. Now let's look at some electrochemical reactions, right? Electrochemical corrosion. Electrochemical corrosion. Corrosion. So for electrochemical corrosion, we can consider similar cells, right? So when zinc reacts with 2HCl, giving you zinc chloride plus hydrogen gas. You can break this into cathodic and anodic reactions, which means that it involves only hydrogen. You can do that, we did that. And we have when also zinc reacts with sulfuric acid. When we react with sulfuric acid, we're giving you zinc sulfate plus hydrogen what? Gas. We also have, when you separate this, let's do this one. For the separation, let me use different one. Okay, let me do iron. When iron react with what? Hydrochloric acid. Do here, giving you iron chloride plus hydrogen gas. So let's try to separate this in the anodic and the cathodic. So in that, when this, for this one, you know that in the anodic reaction, the anodic cell, that's a half cell anodic, we are going to get zinc giving you zinc 2 plus what, 2 electron. And for, let's take the third one, we're going to get iron giving you iron 2 plus 2 electron, right? And then when you go to the cathodic reaction, you also do that. But note that for the general anodic reaction, we have it that M, let's take note of this, N plus Ne for the general anodic reaction. Now let's look at some corrosion resistant metals. Now when we talk about corrosion resistant metals, that means that they resist corrosion, but that's not true. They undergo corrosion, right? They undergo corrosion, but what they do is that they form a passive layer. For the precious metals, right? Gold, silver, platinum are found in nature in their metallic state, right? So in their metallic state, it means that they are in their stable state. So they are stable. That's why they don't undergo corrosion. They are stable. You get it? But what do these metals have in common? These metals, they are corrosion resistant metals. That means that when they react with oxygen, they form an oxide layer, and this layer prevents further deterioration, or it reduces the rate at which corrosion will happen. Now let's take iron. Iron corrodes, right? Why? This is because iron also forms passivation layer, but in this case, the passivation layer of iron, that's the hematite or iron, is porous. So we have Fe2O3. The passivation layer form on it. For example, we have this metal. This is a metal ion, and this is a surface. The passivation layer is porous. So then corrosion increases. The rate of corrosion will increase. But from aluminium in its natural state, when we react with oxygen, it's formed alumina. And with alumina, the passivation layer is not porous. So the rate at which corrosion will happen will be slow. That doesn't mean that aluminum doesn't corrode or stainless steel doesn't corrode. They corrode, but they form a passivation layer which prevents or which slows down the rate of corrosion. Let's look at something. Corrosion resistant metals. We have anodized. When we talk about anodized titanium is that you intentionally forming a passivation layer on the material. So you have for you to reduce the rate of corrosion, you intentionally form a passivation layer on the material to prevent or to reduce the corrosion rate. That's it. And this is stainless steel frame. You know that. Now let's look at classification of corrosion. We have 3 major classifications of corrosion: the nature of corrodant, mechanism of corrosion, and appearance of corrosion. So the nature of corrodant, is it wet or dry? So we have is wet corrosion or dry corrosion. We have the mechanism of corrosion, whether chemical or electrochemical. And the appearance, whether it's uniform or localized. Let's take note of it. So let's brief on that. So when we look at the nature of corrodant, right? Atmospheric corrosion is the deterioration and destruction of materials and its vital properties when exposed to air and its pollutant, rather than immersed in a liquid. That is atmospheric corrosion. So here, classification. Dry is at what? A very low humidity. That's the classification of atmospheric corrosion. We have damp, which is between, and wet, associated with dew, ocean spray, rainwater, and other forms of splashing. Let's look at what nature nature of corrodant. Atmospheric corrosion can occur in the following. In the rural areas, you know that it's less corrosive, do not contain, because they are not factory. A lot of factories there do not contain organic and inorganic particulates, and principal corrodants are moisture, oxygen, and carbon dioxide. The urban, similar to the rural type, with little industrial activity. So with the rural, they have activities. Contaminants include the SOx and the NOx. Varieties from motor vehicle, domestic fuel, right? Yeah. Now we have the industrial one. We have associated with heavy industrial processing. There is high concentration of sulfur dioxide, chlorides, sulfate, and nitrate, and this all facilitate to corrosion, increase the corrosion rate. We have the marine windswept chloride, and this chloride also facilitate corrosion, which are deposited on the surface of material. Highly corrosive, strong, depends on wind and direction, and equivalent environments created by the icing. So the use of what? The icing of salt on the road. Let's look at time of wetness, factors influencing atmospheric corrosion. So we are talking about atmospheric corrosion. We have time of wetness. Directly determines the duration of electrochemical corrosion processing. It depends on humidity. So when there is increase in humidity, percentage of humidity, there's increase in time of wetness, whereby it increases the corrosion rate. You understand? Yes, and the corrosion rate, let me show you the effect of humidity on the corrosion rate. So we have the humidity, which is in percentage. And as the humidity increases, the corrosion rate also increases. But at 70%, pollutants cannot affect the corrosion rate. It will just increase. Whether with or without pollutant, the corrosion rate increases with humidity at 70%. Now, if there are certain gas which also increase the corrosion rate, for example, we have the NOx and the SOx. The NOx and the SOx, it increases the line of corrosion rate. So when in the environment then it's humid and then there's the NOx and the SOx inside, it tends to increase the corrosion rate. So this is a corrosion rate against the humidity. So sulfur dioxide produced from combustion of sulfur containing fuel, fusel fuel, it has high solubility in water. It forms what? Sulfuric acid, and in the surface of moisture film. So sulfuric acid is very corrosive to certain engineering materials, and when it comes to that, since it's corrosive, corrosion happens. This is electrochemical corrosion. Let's still be, and chloride, chloride to the seaside, it increases atmospheric corrosion rate. Like we have the surface electrolytic formation of hygroscopic salts such as sodium chloride and magnesium chloride, and it increases the atmospheric corrosion rate. We also have the other atmospheric contaminant, hydrogen sulfide, hydrogen chloride present in atmospheric intensify corrosion rate. Temperature, effect of temperature on the atmospheric corrosion rate is complex. Yes, this is because it can increase or decrease. Determine this is because when there's temperature increase in the environment, now there will be at a point that oxygen will be out of the system, and if oxygen is not in the system, what happens? Corrosion rate will decrease. That is the same thing affects when it's also at a very low. If you are saying that corrosion, if at high temperature corrosion increases, at low temperature corrosion doesn't increase. But at certain low temperature, because of evolution of oxygen gas, corrosion also will increase. So that's why the corrosion rate can increase or decrease, right? Now we'll look at the last thing, which is the appearance of corrosion. The appearance of corrosion can be uniform or localized. And the localized, we have two, which is the macro, which can be seen by the eye, and we have the micro, which cannot be seen by the eye. Now, example of the localized corrosion, which cause localized appearance of corrosion, is we have the patent corrosion, we have the galvanic corrosion. We have a lot of them. So with this, we are going to talk it in the next lecture. Thank you very much for watching this video.